Hello. So today let's discuss the chapter 16, which is the equilibrium and welfare. Okay. So I'm gonna skip several chapters on the textbook of MWG and to continue on this concept called equilibrium and the welfare, which is a sort of a continuation on the production theory. And later, if we have chance, we can update some series on the other parts, such as the choice under uncertainty and so on and so forth. Okay, good. So in this chapter, we're gonna select several topics. So in the beginning, we need to define the equilibrium and welfare, and a very important concept in measuring the social welfare, which is called the Pareto Optimal, okay, or Pareto efficiency. Okay, so that's gonna be 16 point B. And in point C, we're gonna introduce the first fundamental theorem for the welfare theory. Okay, and then we're gonna introduce some properties in Pareto optimality, and also gonna discuss the related social welfare optima. Okay, which is closely related to Pareto optimal. Good. So let's begin with the definitions first. Okay. Okay. So in 16 point B, so let's study for economy. Okay. So we're gonna have the capital I of consumers. So here from here on, and we're gonna combine the consumers and producers together. Okay. And there are J firms or producers. Okay. And there are L commodities, okay, or L goods. Okay. And the commodity, they can be consumption goods, or they can be inputs or outputs from the firm. Okay. So we're gonna say that each consumer from from 1 up to capital I, okay, we're gonna characterize the consumers by a consumption set. So we're pretty familiar with this. So that'll be the consumption set Xi as a subset of RL. Okay. And a preference relation defined on Xi. Okay. And which is assumed to be rational. Okay. So it means that it's complete and transitive. Okay. So that's the aspect for the consumers. So how about the firms? So we're gonna have, so this will be the consumer, okay, and this is for the firms. So the firms, for each firm J, from I up to capital J, so this is gonna be characterized by some technology, right, or production set capital Y, as we mentioned before. Okay, so taking some input to get some output, right? And here we also have some basic assumptions that this is non-empty and closed. Okay, good. All right. And so beyond those things, okay, we're gonna have something new, which is called the endowments. Okay. So it's sort of like savings, or the saved money for each consumers, right? So that the consumers, they can consume either something to buy something new, or just use the to buy something new produced from the firms, or just to consume the endowments, that is like the saved money or the saved goods. Okay, endowments. Okay, this would be represented by this Greek letter omega, so that would be also a vector. Okay, so be careful, don't mix this omega with W, which is the wealth. Okay, omega 1 up to omega L. Okay, all right, good. So the basic data or the observation, okay, or just the sort of the space on the preference, technologies, and the resources or the endowments for this economy. So basically, we're gonna represent the economy as a tuple. Okay, so we have the first will be the consumption set X and preference relation for each consumer from I from 1 to capital I. Okay, for the firm J up to capital J for the technology and endowment vector. Okay, from 1 to L. Okay, so all right. So here, this is representing the economy using this tuple. Okay, and we're gonna say that we can say that an economy is a pure exchange economy. Okay. If its only technological possibility is that of free disposal, okay. If Yj is minus R plus L. And for all J from 1 up to J, okay. Where in this economy, there's just only pure exchange, okay. So it means that all the consumptions are from the things produced and all the production is sold to the consumers to consume, okay. All right, good. So let's make the first definition, okay, for an allocation. So that's going to be 16.b.1. So basically the traditional economics, so this subject is concentrating, or the main topic will be the study on allocations, or the most efficient allocations, okay, or different kinds of allocations. And you can see that in modern economics, people are tending to study more about individual decision makings and maybe based on some constraints. So those are different topics in the microeconomics histories, right? Okay, so say that an allocation, okay, xy, okay, from x1 up to xi, y1 up to yj is a specification of a consumer vector xi for each consumer from 1 up to capital I. And so that'll be a consumption vector, okay? Consumption vector X and production vector and this Y is a production vector Y for each firm J from 1 up to capital J. Okay, so that would be called an allocation. So just a combination or a concat of those two tuples, okay, with consumption and production. Okay, so we call this allocation XY, we call that feasible if the summation over all the i's for xli to be, we can consume, as we said, the endowments for each L, good L, or we can consume something produced from the firms. Okay, so that's it. And for every good L. Okay. Alternatively, that would be the summation over I, xi, if we sum over, so if we present this in the vector of L, okay, then this will be in this form, okay? Essentially, they are the same thing. Just this will be using the vectors in L dimensions, but the previous one was not like this, okay? Good, so we can denote the set of feasible allocations by the following, okay? So the set of feasible allocations. So this A is the set of those xy's. So we're gonna cross all those x's and also cross all those y's. Okay, where we have this requirement satisfied. Okay, so the endowments or the production to be consumed. Okay, and as a subset of L commodities times I plus J people, okay, or the individuals. Okay, good. So the notion of a socially desirable outcome that we're gonna concentrate on is that of a so-called Pareto optimal allocation or Pareto efficient allocation, okay? So that leads us to the definition of 16.b.2, which is about Pareto optimal, okay? So we call a feasible allocation xy is Pareto optimal or Pareto efficient, same thing. Okay, if there is no other allocation x prime, y prime, also in the set of A, that Pareto dominates it. So in other words, what is Pareto dominance? So it's if there is no feasible x prime, y prime, such that, so the meaning of Pareto dominant or Pareto efficiency is that there's no some other x prime, y prime, which is very feasible, and we're gonna have, for person I, is at least good as x prime in consumption xi prime, that is weakly preferred to xi for all I, and at the same time, for some other people, we have the strict preference over xi for some I. Okay, so this means that a Pareto dominance means that there's no feasible some allocation x prime, y prime, such that we're gonna have all people, they are not going worse, but there are some, at least some people, they're strictly better than before. Okay, that would be called Pareto dominant. But we're gonna say that there's no other allocation that Pareto dominant the previous one, then this is called a status of Pareto optimal or Pareto efficient. Okay, good. So that is the Pareto efficiency or Pareto optimality. So next, okay, we're gonna describe a kind of economy called private ownership economies. Okay. So this will be a very straightforward idea. So the private ownership simply means that each firm is owned by all those consumers. Okay, it's just maybe some people they have a bigger share, or some people they have a smaller share of a firm, but maybe some people they do not have even a share of a firm, right? So that's very realistic, and this is called privately owned, right? And this will be just simple for the characterizations, right? Okay, good. So, and in this case, we can sort of concentrate more on the consumers, right? Because we're gonna assume that consumers they more or less own all the firms, right? It's just then we can just discard all those firms and concentrate on the individuals' decision makings, right? So the firms they're just owned by the people. So at the end of the day, then it's just we're studying all those people or all those consumers, right? Because they're just the firms are just are owned by themselves and just they're making some stuff for themselves to consume, right? Okay, good. So that is basically the intuition of this. Okay, so formally, okay, so we're gonna formally describe this. So consumer I, okay, has an initial endowment of vector of commodities, omega L, omega I, okay, which is an element of RL. So this would be a vector, okay, and a share theta ij, so person I to firm j. So the share will be just a proportion of the profits. Of firm j. So this is an interesting framework, right? So you can see from some fundamental ideas from accounting from here, right? Okay, so we're omega will be the summation over I of those omegas. And we're gonna say that the theta summing over I has to be 1, right? And it is true for every firm J. Okay, so then we're gonna rewrite our economy in the sense of this private owned economies. Okay, so the economy is gonna be a tuple. First, the consumer again, xi, preference, and from 1 to capital I, and the producers, firms, from 1 to j. Okay, and then the endowments and the shares. Okay, omega I, theta I1, and theta I2 up to theta Ij for firm J. And this is for each person I. Okay, good. This is long, but it's very straightforward, right? So the notion of a price-taking equilibrium for a competitive private ownership economy is called a Walrasian equilibrium. Okay, or called a competitive equilibrium. So essentially, it's requiring some proper price. Okay, so we're gonna need some price to make this equilibrium hold. Okay. Okay. So let's define the Walrasian equilibrium. So that'll be definition 16.b.3. So in a private ownership economy, okay, specified by, okay, let's say you call this as capital E, okay, specified by this capital E. Okay, so in allocation X star, Y star, and a price vector P for all the goods from P1 up to PL. Okay, so this constitute, okay, we often say this word, okay, constitute a Walrasian or called competitive equilibrium if we have the following requirements satisfied. Okay, so the first one is gonna be for every firm J, so the production Yi maximizes profits in the technology Yj. So that is P in a product Yj less than or equal to P in a product Yj star. Okay, so this Yi is just solution to this PMP problem, right, for all Yi. Okay, and similarly for the consumers, okay, for every I, Xi star is Xi star maximizes the UMP problem for the preference relation in the budget set where Xi such that is P in a product Si less than or equal to P. So the money that each person got is the first endowment P omega I plus all those shares from all the firms that this person has. Okay, so that's gonna be theta Ij P Yj. Okay. All right. Okay, so the last one would be asking the given the conditions between including the endowments and the consumption and all the production. Okay, so we're gonna say that the summation over I for Xi stars. So this had to be exactly omega bar plus the summation over J for all Yj star. Okay. So this is very straightforward that all the consumptions are from either which are the endowments or which are produced by the firms. Okay. Good. So that'd be a private ownership economy, and this would be a definition for a Walrasian equilibrium. Okay, So here we can observe that a key part of this definition will be this price, right? So we're gonna have to find such price vector, and of course allocation of x star and y star, so that we can obtain such Walrasian or such competitive equilibrium, right? Okay, so that's the introduction to this Walrasian equilibrium, and later we're gonna show some properties and establish some results related to this. Okay. All right. So that'd be the section in 16.b. Okay. So now let's move on to 16.c to talk about the first fundamental theorem of welfare economics. Okay. First fundamental theorem of welfare economics. Okay. So this first theorem of welfare, it's essentially something about the conditions under which any price equilibrium or the Walrasian equilibrium with some money transfers, because so we didn't mention the equilibrium with money transfer. It's just a more general version of the Walrasian equilibrium. Okay, so we can consider this as something just as the Walrasian equilibrium, and especially in particular with this Walrasian equilibrium is that would be we're talking about the conditions when we have this equilibrium to be a Pareto optimum. Okay, so that's essentially what we're talking about in this theorem. Okay, so before this, and of course we're going to assume that there is local non-satiation for the preferences. Okay, and this is important to have for those results. Okay, so we're going to have, before the theorem, we're going to have first have a definition. Okay, so that's still something about the local non-satiation. Okay, we might have seen this a lot of times, but here we're going to just have a quick recap. So we're going to say the preference relation on consumer set at xi is locally non-satiated if for every xi and every epsilon there is an xi prime such that it's pretty close to this xi, and it's strictly preferred than xi itself. Okay, so again, intuitively, this local non-satiation, it says that, so this would be satisfied if there's some desirable goods or commodities. Okay, all right, so that'll be just used for the mathematical properties, right? Okay, so next we're gonna go to the proposition 16.c.1, which is the first fundamental theorem of welfare economics. Okay. Okay, good. So I'm going to say that if preferences for each I are locally non-satiated, okay, and if the allocation x star, y star, and the price, so this tuple is a price equilibrium, or the Pareto, or the Walrasian equilibrium. Okay, so we're gonna just skip this part with the transfers. Okay, we didn't mention that, but we just consider this as the Walrasian equilibrium because that would be a special case. So the general is true, so this special case must be true. then the allocation x star y star, and you can refer to that part for the money transfers, right? So for the reading on the textbook. So this x star y star is Pareto optimal. Okay. All right. Good. So now let's prove this. Okay. Okay. So the starting point is that, so now we suppose this x star y star p is a Walrasian equilibrium. Okay. With wealth level from, so this would be not, this is not omega, this is W1 up to Wi. Okay. Okay, so and remember that in the definition of the Walrasian equilibrium, we have this summation over I of all the W's we're gonna have to be either from the endowments or from the productions, right? Okay, so and so the preference maximization part of the definition of an equilibrium with so either with transfers or not. So this simply gives us that okay, if xi strictly preferred to xi star, then p in the product xi, this has to exceed the budget that we have, right? And this is very straightforward. Okay. And by the local non-satiation, okay, and if xi radically preferred to xi star, then p x I gonna be greater than or equal to Wi. Okay. So anything that is at least as good as xi star is at best just affordable. Okay. Good. So now let's consider an allocation xy that Pareto dominates x star y star. So we're gonna use the contradictions. Okay, suppose we have this, okay, and that is xi weakly preferred to xi star for all I, and must also xi strictly preferred to xi star for some I, okay, by the definition of Pareto dominance. Okay, and then we must have, so from the above, then we have P inner product xi to be greater than or equal to Wi for all i's, and by the other one, we have P xi strictly greater than Wi for, this is for some, for all i's, for some I, okay? So we're gonna sum over all the i's, so P in the product xi, so that's gonna be strictly greater than the summation of Wi, which has to be the P this would be the omega, okay, plus summation over j p yj star, okay. And now we have this, okay, and in addition, because yj star is profit maximizing, right? The solution to the PMP for from J at price P, okay? So we're gonna have P inner product omega plus summation over J, P inner product yj star to be greater than or equal to P inner product omega plus summation over J, P, but inner product with yj, no star, okay? And then the summation over I, P, xi, this would be greater than P omega plus P yj, okay, from all the above. But this means that this xy cannot be feasible, right? Cannot be feasible, okay? And in other words, the summation over I, xi equals omega plus summation over j, yj. This implies summation over I, p, xi equals p omega plus summation over j, p, yj. And this contradicts this, okay? And then we conclude that the equilibrium allocation, so x star, y star is Pareto optimal, okay? All right, good. So that'd be the proof for the first fundamental theorem of welfare economics, okay? Good. So, and from here we can see that once we're given some Walrasian equilibrium, right, and we're gonna know that this allocation x star y star, that would be Pareto optimal, okay, and that's guaranteed by this first welfare theorem. Okay, good. So the next thing we're gonna talk about for today, so we're gonna skip the second welfare theorem, okay, so you can have a look on the textbook if you're interested. So the next thing we're gonna discuss will be the some properties that we have for the Pareto optimality, okay. Good. So the next is gonna be 16.E, and where we talk about Pareto optimality and also talk about social welfare optima, okay. So here we're gonna discuss the relationship between the Pareto optimality and the maximization of a social welfare function, okay. So we're gonna also further define this, okay. Okay, so now we're given a family, okay, of a family which is called UI of continuous utility functions, and representing the preferences of I consumers, okay. then we can capture the attainable vectors of utility. So essentially this UI, so we're gonna later, okay, so let's first finish this. The attainable vectors of utility levels for an economy Okay, so we're gonna have this economy as before. So where we have the consumption set, preference, and okay, and we have this production Yj, and I'm gonna have this omega. Okay. So specified by this by means of the utility possibility set. Okay, utility possibility set. So that's gonna be okay where we have this U, okay, capital U. So this set is some set where we include all those families of utility functions, U1 up to UI, okay, such that there is a feasible allocation such that UI less than or equal to UI xi for I from 1 to I. Okay, so essentially what we're talking about here is given some xi's, okay, for each consumer's consumption, and with this utility UI, we're gonna have, so this is a function, okay? So this level of this UI, and we put that in this family and in this set. So that's gonna be this utility that we have in this utility possibility set. Okay, so where we have this this relationship. Okay. Okay, so and then with this, we're going to define another set called Pareto frontier. Okay. Definition for Pareto frontier. Okay. And that's called UP. So this UP set is also a family of those continuous utility functions where this are in that U, okay, the one we just defined, such that there is no such U1 prime up to UI prime in U, such that UI prime is bigger than or equal to UI for all I, and UI prime bigger than UI for some I. And this definition is very similar to the definition of Pareto efficiency, right? So here it's just in terms of, we're talking about utilities, and those are just the possible utilities that each person can get. And we cannot have sort of to let each person to have some greater utilities and keep all people having the same utility as before, right? So that just, or sort of an alternative way to restate the Pareto efficiency. Okay, those are essentially the same thing. Okay, so and for example, okay, So for example, let's have a little figure, okay? So which is also given on the textbook. We're gonna have U1 and U2, okay? So this set of U is sort of like this, okay? So all those areas, this is in the set of BQ, okay? And this is an example of a convex utility possibility set.